It's finally here, the last lesson of the semester. So lesson 8 is talking about chemical bonds. When atoms of elements get close, the protons from one atom can attract the electrons of the other atom enough to hold them together in something called a chemical bond. And we're going to talk about the two different kinds of chemical bonds. So chemical bonds are very much stronger than the attractive forces between molecules that we talked about before when we were doing our physical changes. When we talked about physical changes, we talked about liquids and solids having some attractive forces. These are much, much stronger, strong enough to, so takes much more energy to separate the atoms within a molecule than it does to separate two particles from each other in a solid or a liquid. So melting solid from solid water to liquid water is going to take a whole lot less energy than actually taking a water molecule and splitting it up into hydrogen and oxygen gas. So we're talking about what is holding together these atoms in a compound. Review that we talked about the valence electrons in lesson 7, and the valence electrons are key to bonding. Remember, the valence electrons are those in the outermost occupied orbit. Atoms will lose or gain valence electrons to form ions with a full orbit. We talked about that in lesson 7. We said that the metals are going to lose all of their valence electrons, and the nonmetals are going to gain electrons in order to have a full orbit, which is usually 8 valence electrons. In this lesson, we're also going to see that another way that atoms can attain a full orbit is to share valence electrons. So let's take a look at these. This is the dot diagram diagram model of the atoms. So I just want you to kind of take a look at these and try to figure out, these are the dot diagrams in this final column, and what are the letters in the dot diagram representing? And then what are the dots in this dot diagram? What are they representing? And what is the maximum number of dots that can be on one side of the letter? So one side meaning top, bottom, left, right. So you can pause the video and try to make an assessment on that. Okay, hopefully you figured out that the letters in the middle is the chemical symbol. So that's representing the atom of lithium, or that in the case of Mg, the atom of magnesium. And the dots are representing the valence electrons. Note that if I have one valence electron, because lithium's in group 1A, I have one dot. 2 valence electrons, I have 2 dots. 3 dots. 4, 1, 2, 3, 4 dots. 5, all the way up to 8. And the maximum number of dots on one side is 2. Notice that the most I can have is 2, 4, 6, 8 total, which is 2 electrons on each side. So when we do the dot diagram models, we're going to look up the group number of the element. So remember, the group number is equal to the number of valence electrons. And then you're going to place one dot, which is representing a valence electron, on each side, top, right, bottom, left, of the element symbol until it has the correct number of dots. And it doesn't matter, you can start with any side, and you can fill sides in any order as long as each side has only one dot until all 4 sides have one. So you're not going to pair up any dots until you're on the 5th dot being put down. So hydrogen would look like an H with 1 dot. Calcium would look like a Ca with 2 dots. And again, these 2 dots, it could be on the left and the top, or on the bottom and the top, or the left and the right. It doesn't matter which 2 sides. When I'm done, a proper calcium dot diagram should have 2 sides with 1 dot each, and 2 sides that are empty. Fluorine has 7 dots, 3 sides with 2 dots, and 1 side with 1 dot. Sulfur has 6 dots, 2 sides with 2 dots, and 2 sides with 1 dot. So in our bonding model, atoms are going to tend to gain or lose electrons in order to have the same number of valence electrons as the nearest noble gas element. So will elements in group 2A gain or lose electrons to form more stable ions? What charge do you think the ions in group 2A have? And as an example, what do you think the dot diagram for calcium 2+ ion is? And will the elements in group 7A gain or lose electrons to form ions? What charge do you think the ions in the group 7A have? And what do you think the dot diagram for fluoride is? Again, pause the video and take a shot at this on your own before you look at the answer. Okay, so let's look at calcium. Calcium is a metal in group 2A. The fact that it's a metal is going to tell me it's going to lose its valence electrons. The fact that it's 2A means it had 2 valence electrons to begin with, so that tells me what the atom dot diagram looks like. But when it forms an ion, it's going to lose both of these electrons. It's going to become 2+ charged, and now I'm going to have a calcium 2+ charge. Notice I have no dots over here. On the other hand, fluorine is a nonmetal. It's in group 7A, so it has 7 valence electrons. And because it's a nonmetal, they gain enough valence electrons to have the same number as the nearest noble gas. That's normally 8. So we say gaining enough valence electrons to have 8. So in this case, it needs 1 more. And when it gains that 1 more, that gives it a -1 charge. Now, I can consider what's going to happen when I start pairing 2 of these together that are going to each form ions. So I have metal atoms transferring valence electrons to nonmetal atoms. So one version of this is I look at a lithium, and here's the full orbit dot model. Lithium has 3 electrons. It has 1 valence electron in its outermost ring, which is the second orbit, and it's going to lose its valence electron, and that electron is going to go over to fluorine. Fluorine has 7 valence electrons. It needs 1 more to have a full valence shell, so it's going to get it from lithium. Another way of looking at it is using this dot diagram model, which is probably much easier, and I see the hole up here for fluorine where it's missing 1 electron, and I see that lithium has the electron, and I'm going to use an arrow to sort of indicate what can happen as it bonds, that it's going to go from lithium over to fluorine. When I'm done, in this version, I see that fluorine has a full valence shell, and it has a total of 10 electrons, but it only has 9 protons, so it has a -1 charge. Lithium has only 2 electrons, but 3 protons, so it has a +1 charge. Here, I'm just showing that this no longer has an electron, and it has a plus charge. And here, I've left it blue just so you can see where it went to, but normally you just leave them the same color black. Fluorine now has a full valence shell with 8, and it has a negative charge. And again, the way I know that it's going from lithium to fluorine is because lithium is a metal and fluorine is a nonmetal. So if we look at these, let's see if we can observe the patterns. What type of atoms, metal atoms only, nonmetal atoms only, or a combination of metal and nonmetal atoms are involved in this ionic interaction? And what happens to the metal atom's valence electrons when an ionic interaction forms with a nonmetal atom? And the lithium plus ion has the same number of valence electrons as what noble gas? What about the fluoride minus ion? How many electrons, what is its nearest noble gas? And why do you think the compounds formed by these interactions are called ionic? And why will these 2 ions, lithium +1 and fluorine -1, be attracted to each other? So take a second, see if you can answer those on your own. Okay, so as we sort of stated, and hopefully you kind of go back, and if not, rewind and kind of look at those pictures again, but these are happening between metal and non-metal atoms. The metals are going to be the ones that are going to give up the electrons, and the non-metals are going to be the ones that gain the electrons. And again, the metal atom's valence electrons are being transferred to the non-metal atom, and they both become ions. The lithium ion is going to have the same valence electrons as its nearest noble gas, which is helium. It has 2 electrons. The fluoride ion has the same number of valence electrons as neon, which has 10 total, but it also has 8 valence electrons. And the compounds are called ionic compounds because once this transfer has taken place, both of the atoms have become ions. One's a positively charged, one's a negatively charged. And they will be attracted to each other because they're oppositely charged, so they're held together by the fact that they're opposite in charge. Here's another way I can sort of show these. Note that one of the things on the top it's unbonded and on the bottom it's bonded, and then over here we have the formula of a compound. So let's kind of stare at these for a while and kind of answer these questions. The question number one is, what is the overall charge of the compounds? Compounds mean once it's bonded. What do the subscripts in the formula represent? That's over here. How does the dot diagram for aluminum oxide, that's this one, help you understand why 2 aluminum atoms are needed to combine with 3 oxygen atoms? Why isn't it not 1 and 1? Why is it a ratio of 2 to 3? So take a second and look at those. Oops. Okay, let's go through the answers. So the overall charge, this is a -1. This is another -1. I tried to put a negative sign bigger than the original one. The original one was kind of lost. So this is 8 electrons and a negative charge, and this one's 8 electrons and a negative charge. So I have a positive charge. So -1 plus 2 would be +1 minus 1 is back to 0. So this has 0 charge. This one is -2 plus 3 would be +1, minus 2 would be -1, plus 3 would be +2, minus 2 would be 0. So when I'm done, these add up to 0. How does the dot diagram for aluminum oxide help you understand? Oh, what does the subscripts represent? These subscripts represent is how many I have. Notice that this has 1 calcium ion and 2 chlorine ions. So the 2 means that I have 2 of them. Now we've already seen our compound formulas and we know this, but it's kind of reminding us what's happening. Down here I have 2 aluminums, hence the 2, and 3 oxygens, hence the 3. And hopefully we can understand why I need 2 aluminum ions to combine with these. If I look at these aluminum atoms at the beginning, they each have 3 electrons. And so they want to give up all 3. And when I look at the oxygen atom, it only has room for 2. So I see that these 2 can go to this oxygen, and then I have 1 left over, but 1 is not enough. So I put 1 going to this one, but it's not quite enough. So it needs to have another one from another aluminum atom, which then has 2 left over, so it goes to another oxygen atom. So in other words, the total number of valence electrons that the metals are giving up, which in this case is 2 atoms times 3 valence, so 6 electrons, has to be the number of electrons that are being gained by the oxygen atoms. This one gets 2, this one gets 2, this one gets 2, for a total of 6. So I have to have a neutral compound. These charges have to cancel out, which will happen when I have the right number of electrons moving. Okay, let's talk about a different kind of bond. So that's the ionic bonds. A different kind of bond. Before we just kind of want to back up and talk about, remember, each atom has protons in the nucleus and an electron cloud. So protons are positive, electrons are negative. So I have, between 2 atoms that are next to each other, I actually have 4 interactions going on. I have the electrons on the left attracted to the protons on the right. I have the protons on the left attracted to the electrons on the right, and those are both attractive forces. Then I have the protons on the left are repelling the protons on the right, and the electrons on the left are repelling the electrons on the right. So I have 2 repulsive forces and 2 attractive forces. Okay, so in forming a covalent bond, I want you to notice what's going to happen if I move those electron clouds closer to one another. So when I do, I now have these 2 electron clouds are closer to one another, and this electron cloud is closer to this proton on the right, so this has gotten stronger because now as I've gotten closer, it's a stronger attraction. And this electron cloud is closer to this nucleus, and so this has gotten stronger. So this attractive force has gotten stronger. But as a consequence, the electron clouds are repelling more. So this has also gotten stronger. But I didn't move the protons, so this repulsive force did not get affected. So overall, I've increased the attractive forces here, I've increased the attractive forces here, I've also increased the repulsive forces here, but I didn't have a change here. Yet overall, it ends up winning. This is a net gain of a pot more attraction between these. So this ends up being a stronger attraction between these two atoms if those electron clouds move. And that's what really happens in a covalent bond. I'm going to show it a little bit here. In this case, what we're really showing is that the nonmetal atoms, the valence electrons are going to shift closer to be shared between atoms, as if each of the atoms gained an electron. So here I'm showing them unbonded, and I've circled the ones so that you can kind of focus on them. As I bring these two clouds closer together, and we usually just draw the whole atoms closer together, we see that now they're sort of overlapping. So one of these came from the right one, and one of these came from the left one, but together they're sort of being shared. So these two look like they're in this outer orbit of the left one, and these two also look like they're in this outer orbit of the right one. So it's kind of double accounting. I'm counting them twice. I'm counting them once in this set and once in this set. In this case, I can do it more than one time. So here's an H atom and an oxygen atom, and here I have a pair of electrons that can be shared, and here I have another pair of electrons that can be shared. So the hydrogen has one electron that it can share, and it needs two total to be like helium, and the oxygen has 6 valence electrons, and it needs 8 total to be like neon. And so here it gets one from this hydrogen and one from this hydrogen, but it's not transferring. They're overlapping and sharing. So it's a different mechanism that results in the same thing, except that now I have no ions. Because I didn't actually transfer the electrons, both the hydrogens and the oxygen are neutral. Same thing with the fluorine. So I don't have ions here, but I get the same effect. Here I have a more complex one. Here's a nitrogen with 3 hydrogens. Again, each hydrogen can gain 1 by sharing 1, and the nitrogen has 3 unpaired electrons that it can gain. And so I see as they get closer together, I form these covalent bonds. Now another way of drawing this that's a little less congested is to use these dot diagrams. There's a whole lot less circles and stuff going on. And as I draw them together, so here they're unbonded, I can see, okay, this has a space for one more, and this has a space for one more, and this is ready to be paired. It's not paired up, so this one is ready for pairing and this one's ready for pairing. If I draw them closer together, I can see that now they're being shared because they're between the two atoms. I can also replace this shared pair of dots with a line that just makes it a little less congested. I tend to like that. This represents a covalent bond, which is a shared pair of electrons. Here I have that same water, H2O, and I can see that oxygen has need for 1 over here and 1 over here. And when I push them together, I can see that, okay, this is a shared pair and this is a shared pair. Here is the this is a covalent bond, and this is another covalent bond over here. And in the NH3, I have, as I move this one over to here, this is going to become a shared pair. As this one moves over to here, this is going to become a shared pair. And as this one moves down to here, this is going to become a shared pair. So this one, and this one are shared pairs. Notice there was 2 on the bottom that didn't get affected. So we have 1, 2, 3 covalent bonds, and then another pair of electrons that was there that never was affected. So instead of drawing these orbits in this manner, what we do is we just draw the valence electrons as dots, and then we're going to covalent. We can draw either the covalently bonded pairs of electrons as lines, or just as 2 electrons that are right next to each other. I like the lines a little better. Okay, let's see if we can notice these patterns and answer these questions. What type of atoms, metals atoms only, non-metal atoms only, or a combination of metal and non-metal atoms are involved in covalent bonds? And remember that hydrogen is considered a non-metal. Even though it's to the left of the staircase, it's considered a non-metal. What is happening to the valence electrons of the non-metal atoms when a covalent bond forms between them? How many valence electrons does each hydrogen have when involved in a covalent bond? And how many valence electrons do the other atoms have when involved in a covalent bond? So go ahead and take a second, see if you can work these out on your own, and then unpause the video and continue forward. Okay, So these are between nonmetal atoms only. Remember, the nonmetal atoms are trying to gain enough electrons to have the same number of electrons as the nearest noble gas. And so because they need to gain, ends up working well. By sharing them, they end up gaining by, when they bring one to the paired partner, they get to claim both of those electrons as their own. So they end up having unofficial double accounting method of gaining one electron. And the valence electrons are pairing up and being shared between the atoms. So each atom that's next to each other brings one electron to the table to share, and then they get to share both of the electrons. There are two valence electrons in a hydrogen once it's bonded. So when it's bonded, and if you want to go back and look at those, you'll see that they have two. That's because hydrogen's nearest noble gas neighbor is helium, which only has two in its outer orbit. Because remember, the first orbit can only hold two, whereas the other orbits can hold 8, and even at higher levels they can hold more than 8. The other valence, all the other atoms are going for 8. So generally we're talking about trying to get a set of 8 electrons total for the nonmetals, except for hydrogen, it will only go for getting a total of 2. Now, we had talked earlier in the last couple of lessons when we were looking at these patterns, we talked about a property that we called combining power. Now, this is kind of a made-up term that we made up for this course called combining power, but it's a pretty helpful predictor. And a chemical bond consists of one transferred electron or one shared pair of electron, and this is the combining power is basically saying how many types of bonds can it form. Can it form one transfer of electron in an ionic bond or one shared pair of valence for a covalent bond? So in the case of the shared pair, one electron is donated from one atom in the bond and another is donated from the second atom in the bond, remember? And so this is kind of telling me how many chemical bonds it's going to get. So remember, the pattern was 1, 2, 3, 4, 3, 2, 1, 0. So elements in group A will form one bond. Elements in group 2 will form 2 bonds. Elements in group 3 will form 3 bonds. Elements in group 4 form 4 bonds. 5 forms 3 bonds. 6 forms 2 bonds. 7 forms 1 bond. And 8A doesn't form any bonds because remember, those are all nonmetals that already have a full outer shell, so there's no need for any. Again, when we talk about the octet and duet rules, most atoms are going to lose, gain, or share valence electrons to result in 8 valence electrons for each atom in the bond. That's what we call octet rule. Oct, like octopus, and octagon stands for 8. However, hydrogen and helium are going to lose, gain, or share to result in 2 valence electrons. Now, when an atom loses electrons, it actually, remember, when it loses all of its electrons, it has no electrons in its outermost orbit, which means then we're looking at the level below, the lower level, which then would be full. So in other words, if we're talking about something like calcium, when it loses its 2 valence electrons, it has no electrons in the outermost orbit, which I think is the 3rd orbit. I don't have my periodic table in front of me, but I think it's in the 3rd orbit. But the 2nd orbit is completely full with 8, so it still is an octet. When we disappear, when all of the valence electrons disappear, remember the level below it is fully full with 8 electrons, so it still is abiding by the octet rule. Okay, so if we look at this nitrogen, remember, nitrogen has 5 valence electrons, so it is capable, it needs 3 more to get 8, so it's going to make 3 chemical bonds. Hydrogen, on the other hand, has 1, it's going for a duet, it can only form 1 more. It can gain 1 more, or it can share 1 more in a covalent bond, so it's going to form 1 chemical bond. And because of that, I need 3 hydrogens per 1 nitrogen. So in order for nitrogen to get 3 bonds, when hydrogen can only do 1 bond, it needs 3 different hydrogens to do that. And that 3 stands for that there are 3 hydrogens to the 1 nitrogen. We don't use a subscript if there's only one. I mean, obviously, since I see the letter N, I know that there's at least one N atom. So if we don't have a subscript, it implies that there's one of them. Just going to bring up this, but it's not a particularly big idea. The idea that when I form ionic compounds, those are the ones where all of the ions are going to stick together in one huge massive crystal called a crystal lattice. So I don't really have one Na plus and one Cl minus, but I can think of that as being the ratio. If I count all these up, I have as many grays as I have yellows, so it's a 1-to-1 ratio. So I can write the formula as NaCl, but really I should know that it's one huge, all of the positives and negatives are stuck together and it forms one big crystal. Whereas in covalent compounds, those are the ones that form molecules. Because remember, they're just being shared and there are no ions, there's a whole lot less attractive forces between one molecule and another molecule, so the molecules don't stick together. I mean, they're attracted together and they form solids and liquids, but they don't actually chemically bond together like you see. So they're going to be the ones that are the molecular type. Remember, back at the beginning of this unit, we were talking about the molecular type of compounds and the formula unit type of compounds. Well, now I can really say that the ionic ones are the formula unit type and the covalent ones are the molecular type. And I can tell the difference between an ionic compound and a covalent compound because covalent compounds are formed between nonmetals and ionic compounds are formed between a metal and a nonmetal. Okay, so here's a couple of questions to wrap up. Which statement best describes the model for an ionic bond? Formed of atoms of metals, often described as positive ions loosely held in a sea of valence electrons. The bond forms atoms of metals and nonmetals. This type of bonding is often described as one or more valence electrons being transferred from a metal atom to a nonmetal atom, or forms between atoms of nonmetals, described as 2 or more valence electrons being shared between nonmetal atoms. So which one of those is describing the ionic bond? Okay, hopefully we recognize that ionic bonds involve a transfer of electrons that makes ions, and that's going to happen between metals and nonmetals. The next question is the same 3 choices, but is asking which one is the one for a covalent bond? So hopefully you recognize that that's the formed between atoms of nonmetals, and it's the sharing of electrons. The first, we haven't looked at any models that are being described by the first description, although that actually does accurately describe what we call metallic bonding between 2 atoms of 2 metals, but we're not talking about that in this course. So that's the end of lesson 8. There will be, the final homework will be on this material, but that won't be due until after the next test.